We do have a very good colloquium today, I think. Instrumentation is one of those areas that gets less attention than I think it ought to receive. And the person we have today is one of the big names in instrumentation for fundamental physics, David Nygren. Large part of his career in Berkeley, currently at the University of Texas in Arlington. He has been to IFIC before. He works together with the next group. And he will tell us a personal story about developing new forms of instrumentation for particle physics. Everyone knows about the TPC, of course, but then the TPC found applications that maybe no one thought of when they were invented. I'm very keen to hear about all this, and I welcome you on the stage. Thanks for coming.
Hello everyone, it's very good to be back here in Valencia once again. My comments today are really addressed to the younger people in the audience because my message is that there's still interesting things that are likely to be found. I don't know what they are, that's your job, but I want to go over today with what I've learned from looking at the past. If I could wake up my computer here, which was live a while ago. Let's see, here we go. All right, so I actually dislike the word instrumentation. No offense. I think really we will see that there's something that's called the art of experiment, and how gradually it started and how it was launched in various ways, sometimes in ways that were not even imagined by those people who were doing their investigation. So let's have a look. So this is, first of all, a very biased and personal story because I think that's where the human interest is. And if we don't care about something, we're not going to do it. So I'm going to give some examples from mostly other people, but something about what I have done that I think is quite interesting. I did it, so it must be interesting. I'm going to miss, unfortunately, a lot of interesting things about scintillators. I'll use the pointer. Silicon devices, and so my review kind of stops about the time some of you were born, but I still think it's going to carry a message. I borrowed some slides from Michael Hochschild and Eric Wheeler, so let's take a look. Come on. Okay. So I see that there's about 4 different epochs in the story. One might call the first part the Bronze Age. Many particles were somehow inducing visible signals, but finally we reached the point where we could see a single particle. And this began what I'd call the Age of Discovery. This required large amplification one way or another in order to see a single particle. Finally, there was a golden age, which I was fortunate to be part of, where we actually could do just about anything we wanted to find out what was going on in an event. And now we've reached a kind of different era, which I refer to as the megalithic age, where everything is huge. We don't need to go too much further in that because that's the future. So let's take a look. The first thing was imaging techniques. One can divide roughly into 2 categories, imaging and logic, where there's electronics involved. But even at the early time, there was activity in the electronic domain, and I think these old papers are really rewarding to take a look at, and I'm going to show you one of those. So this is a slide I borrowed from Michael Hochschild, I think, and it shows what happened really at the beginning, even before the last century, all up to the point where the intermediate vector bosons were discovered, and then there's much more beyond that. But let's take a look mainly at what happened in this era where instrumentation, if you'll pardon the expression, was developed here, and those discoveries that were related to those developments are pointed out above. So this is a complicated diagram, but it shows, if you look at it, how things change from the beginning, where we finally saw single particles, to cloud chambers, to spark chambers, and photomultipliers, and the Geiger-Müller tube, which I've talked about, nuclear emulsions. Finally, the golden age of discovery with the electronic systems married to gaseous detectors and other devices. So the signals we have come from ionization, scintillation, Cherenkov radiation, sometimes transition radiation, even magnetic induction, and even heat in so-called bolometers. And from those, we want to extract the things we're really interested in. So this is roughly the challenge that we face in the art of experiment. Now, the common principle is some kind of gain mechanism. It can be electronic or it can be something inside the detector, such as an avalanche. But against this, we have to face common enemies, which are intrinsic noise or background from either physical processes or even parts of the system that create noise intrinsically. So we can start perhaps with the spinetharoscope. It was a discovery more than an invention. He accidentally spilled some expensive radium salt on a zinc sulfide screen, and to try to recover it, he looked at that screen under a microscope. He saw rather noticeable flashes of light, which he called spinetharoscope from the Greek word spark. But obviously they weren't sparks, they were just flashes. And when I was a kid, I noticed these very same kind of flashes in the dial of my wristwatch, which had been painted with radium and phosphor, which people didn't understand was dangerous at the time. But I could even see this effect in my wristwatch. The early image detectors were stimulated by meteorological questions, like how do clouds form, examples, and what is the effect of electricity on the droplets that are formed sometimes around dust particles. So in 1888, there was already this kind of gross investigation of phenomena associated with electricity and dust particles. I don't understand how this thing worked at all, but anyway, this is something that was actually critical for the stimulation because it was that interested Wilson, who developed the cloud chamber. And he developed that first in 1895, and this went on for half a century, producing interesting results. So he was interested in meteorological phenomena. He was working at Cavendish at the time, and he built a chamber to play with. And he found that if the ionization, he found that vapors would condense around ionization when the pressure is reduced and the volume becomes supersaturated. And so this was a very productive technique, and many fundamental discoveries involved the cloud chamber. Now, I'm not quite sure how this works, but I guess this is an expansion chamber, and this is the actual cloud chamber up here. So letting some of the gas into a partly evacuated chamber would cause supersaturation here. This is a 1911 example, but many beautiful pictures were made. On the left, we see examples of what happens when X-rays interact, producing electrons which scatter in the gas. And if you don't have everything just right, you get kind of fuzzy images. They fade in time anyway. On the right here is a picture of alpha particles from a source here, illuminated from the side. This is not a brush, but this just shows that the constant energy of alpha particles and their finite range produces a lovely pattern. Now, cloud chamber was used by Compton to discover the scattering of photons, which is known forever now as the Compton effect. He received the Nobel Prize in 1927 along with Wilson for this. And obviously the process is a photon comes in, scatters on an electron, and another photon comes out, which can produce another track that allows one to reconstruct what actually happened. This is an original photograph, which is kind of hard to interpret, but the diagram of what they used is shown here with the X-rays enter here, scatter, and then another electron is produced by the scattered photon up here. So this was obviously a very productive line, and it gave the first true understanding of what elementary particles do when they interact with matter. Now, in 1933, the positron was discovered by Carl Anderson and published. It was discovered in 1932 and published in 1933. This famous picture shows a track entering from below in this image and emerging with less energy because the radius of curvature is smaller than it is here. So something happened, and with the knowledge of which direction the magnetic field is, it was clear that this was a positive charged particle that entered this plate, lost energy, and came out with less. This was the proof that there were positively charged particles, similar mass to the electrons. However, Lacton and Occhiolini had also discovered the positron in 32, but they delayed publication because they were part of Geiger's and Rutherford's group and didn't get credit for it. But even earlier, a Russian named Dmitry Skobeltsyn had observed this same effect, but he didn't publish either. So the lesson here is that one needs to publish a discovery in order to get credit for it. Nobody's ever heard of Dmitry Skobeltsyn. Okay, so about the same time in the 20s through the 30s, Marietta Blau pioneered the nuclear emulsion technique, and here's an example of a spectacular nuclear disintegration, which was discovered through the use of the nuclear emulsions. She worked tirelessly with her assistant, Hertha Wambacher. They were driven out of Vienna in the late 30s in 1938 due to the Nazi transition there. But she continued, and she was instrumental in developing this technique, which led to several discoveries. In fact, the discovery of the pion in cosmic rays led to a Nobel Prize in 1947. Here's an example, hard to see where I'm standing, but the pion comes in here, decays into a muon, and then decays into an electron. And it was seen that they always had the same range and that it was a two-body decay. And it was pretty straightforward to conclude that this was the pion. Also, the kaon was discovered, similarly in emulsion with a kaon track here, densely ionizing because it's relatively slow, came to 3 pions that you see here. Now, Marietta Blau was really written out of the story for a long time, and Powell didn't even mention her in his Nobel Prize. So one can see how this kind of paternalistic bias was quite present in those days. But now she's been given credit, I think, for what she did. In 1952, Don Glaser at Berkeley invented the bubble chamber, and this has been another extremely productive instrument, had a long life and contributed to many fundamental discoveries. Even though I spent many decades at Berkeley, I could never be sure about the story that the bubble chamber was discovered, by either inspecting or drinking a glass of beer. It could be true, but I really don't know the answer. Maybe some of you do, but this was a part of the lore at Berkeley, at least. So here's an example of a heavy liquid chamber in Gargamel, which is instrumental in discovering neutral currents. And then there are many other bubble chambers built. This is the big European bubble chamber in construction. One hopes that the young lady here isn't pushing too hard on this shaft because this looks like it's in delicate balance. And even though the pictures look crowded, it's possible to extract very complicated events and reconstruction that didn't do this one. However, there are many beautiful images of bubble chambers that one can find. Here's one of a K-meson coming in, decaying here into a pion, then a muon, and then an electron that spirals around, complicating the interpretation by overlapping. But one can see how in a hydrogen bubble chamber, the energy loss produces these beautiful images because there's very little scattering. One also sees the evidence of physics where an occasional delta electron, an energetic electron, is produced, curling up in the magnetic field. And probably the most famous bubble chamber picture of all is this one, done at Brookhaven, made at Brookhaven. K0 comes in, K minus comes in here, produces an omega minus, which decays to a cascade, which then decays to a lambda, which then decays into standard non-strange particles. A few gamma rays get converted, and this single event was enough because of the detailed information to establish that the omega minus existed. Of course, there were other examples, but a single event with this level of detail is unambiguous. And you can see that the image, although it's not very well reproduced here, contained plenty of information to reconstruct the event. So the bubble chamber was a really great invention. It had the problem that only a few tracks could be emitted in one event. You can see a number of tracks here. I think I can see it on my computer. But one couldn't put more than a few dozen beam particles in for expansion because otherwise it just got to be too crowded. So the limit of the bubble chamber was that one could only take a few events at a time. And it took years and thousands of kilometers of film to extract the physics. But they died off completely for a while when electronic techniques matured. However, they're back because, for example, a xenon bubble chamber can reject gamma rays by a factor of at least 10 to the 8th. And this is important in the search for dark matter where gamma rays can mimic the nuclear recoil tracks. So the xenon bubble chamber and other liquids are back, showing that they can produce something even now. Now, I'll just take a moment to expand on nuclear emulsions again. They have been used in the opera experiment, searching for the appearance of new taus and oscillations from the CERN laboratory to the Gran Sasso laboratory in Italy. This was done by constructing bricks of lead sheets and emulsions, and with the addition of tracking equipment here, one should point back to where the muons that are seen in this structure, to which brick one should analyze, and with automated equipment one can find where the track occurs. Now, one can't see anything quite at this scale, but if you look at the event in various scales of sight, you can see from this angle. And here's the track in a rotated view, which shows the kink due to the tau being produced and then decays. So the issue here is that sometimes these older techniques can produce the kind of information that can't be obtained otherwise. So now I want to go back to the early time to look more at the electronic aspects, kind of look quickly at the imaging part. But now we go back to Ernest Rutherford and Hans Geiger. They published the first electrical detection of single particles in a philosophical magazine in 1908. And these old papers are really rewarding to go back and find because they are truly letters to friends. And I enjoyed finding them and reading them. For example, Rutherford goes on to say, it has been recognized for several years that it should be possible by refined methods to detect a single alpha particle by measuring the ionization it produces in its path. And this is a picture of their apparatus that they used to do this. This volume contained emanations, including radon. By opening the stopcock, the radon can get in. There's actually a little window here that prevents the radon from getting directly into this part, which has a different kind of gas. And here's a wire that is held at a very positive voltage so that the electrons would be attracted to it, and they would detect the signals. As they went on to say, we had recourse to a method of automatically magnifying the electrical effect due to a single alpha particle. For this purpose, we employed the principle of production of fresh ions by collision, and so on. But importantly here, he mentions the physicist Townsend, who has worked out the conditions under which these ions can produce. So I took the trouble to kind of reproduce this because the language is charming, and it's very interesting to read. I heartily recommend it. So what they did is they could use the signal that was produced to deflect an electrometer so that a spot of light on a distant wall could be detected by somebody looking at that spot. So the electronic detection involved somebody who was watching the movement of an electron, of a spot of beam from an electrometer. So that's how they did it. Later, Geiger, who had been working with Rutherford, invented the Geiger-Müller tube in 1928. This is familiar, but we'll take a moment to look at it here. This wire is not as thick as it looks like in this drawing, but if a track goes through that volume and ionizes atoms and molecules of the gas, the electrons will be drawn to this surface of the wire where the electric field is growing as 1 over r as you get close. At some point, the electron energy is high enough to ionize the other gas molecules, and you get an avalanche process. And this leads to a measurable signal on wire, and these devices are still used today. But it's interesting to note that in the Geiger-Muller tube, the discharge spreads all along the wire, uncontrolled, and produces a very large signal. In contrast, a proportional counter does not have spreading along the wire, so that the avalanche that starts from a single electron here is in some sense proportional to the signal produced in the wire. I mention all this detail because I think they have an interesting consequence. So I learned by chance from the granddaughter of Walter Mueller, who happened to live in the Bay Area, that she knew the true story of how it was actually invented. It was actually more of a discovery. So it turns out that in 1926, Mueller was given an old brass tube with the wire inside. This is called the Spitzenzoller, or spark counter. Geiger had made this in 1913 under the guidance of Rutherford. But he discovered that the Spitzenzoller behaved strangely and produced pulses on its own with varying rate. So clearly it wasn't really understood what the Spitzenzoller was doing. So Mueller paced around the room, unable to understand the strange behavior of his Spitzenzoller. He eventually realized that when he was standing in a certain position, the rate of the Spitzenzoller was greatly reduced. But the effect was reproducible. Now here's something that's important. He made the attempt to really understand what was going on with what he could do, namely move around the room. So the effect was reproducible. He turned around and he opened the door behind him, and he discovered that in the next room a colleague was working with some radium. So he realized that his body has been shielding the Spitzenzoller, and that the Spitzenzoller is detecting the gamma rays from the radium. And so this was a discovery, not really an invention yet. So he tested his device for 5 days, finally showed it to Geiger on the 9th of May, and Geiger exclaimed, "We are the only people who know of this wonderful instrument. We shall make it known," and a host of physicists shall use it. It's almost biblical in its that's the story. So they did that, and now we still have these devices today, as everybody knows, highly refined from the days of the 1920s. So it turns out that the Geiger tube is actually a rather complicated device. You can ask, students should know, well, how does that avalanche spread along the whole length of the wire? This is a question I always ask when I'm giving a course or a lecture on particle technical techniques. And it's often true that nobody knows. I mean, these things have just passed into the lore that Geiger counters work. But actually it's quite interesting because it requires a delicate balance of atomic and molecular physics. It turns out that the avalanche is spread by ultraviolet emitted by the argon in this case. The first excited state is around this, I think that's not quite the right, but it's above the ionization potential of alcohol, for example. It doesn't have to be particular alcohol, but just as long as the energy of that first excited state is higher than the ionization potential. So the excited argon atoms have to live long enough to radiate these photons so that some of them will spread out of the plane of this projection and cause new avalanches to occur along the wire. But furthermore, on the way to the cathode, the ions have to, the argon ions have to be neutralized by charge exchange. Otherwise, when they reach the cathode, they would emit new photons and create new electrons, and the avalanche would never stop. There's a fair amount of complicated atomic and molecular physics that Mueller and Geiger, I'm sure, didn't know at the time. Okay, turning now to another aspect of the electronic world. I'm old enough to know how this circuit works. And what really happens here is that both of these grids in this vacuum tube in the middle have to be sufficiently positive that electrons can pass from the cathode to the plate, producing a negative pulse here. So these are symbolically Geiger tubes here. So this is a coincidence circuit that allows one to tell that, yes, two Geiger tubes or two or more produce signals at the same time. So if you wanted to know that something went through block A, you could have an array of Geiger tubes up here and another array down here. And when you see coincidence, you can tell whether the track was through the block or not, and even have a third row of detectors as indicated by row B. So this led to the Nobel Prize in Physics in 1954. Now this coincidence circuit is familiar to every first-year student of computer science as the AND gate. It's very simple. It's just two things have to occur at the same time. And yet at the moment that both they came up with this, it wasn't so simple. And this is the consistent theme that I've seen, I think, is that things that are not obvious pretty soon become obvious. And I think that's a phenomenon that will continue. So anyway, the coincidence circuit is something we still use today, not just in computers, but in particle physics to tell that the tracks came at the same time. Another enduring technology that came at about this time was the photomultiplier, which are known as PMTs. These were invented by engineers at RCA, and this is an early example of one where one has a photo-detecting surface, a photocathode, in which a photon is turned into a single electron which is accelerated, hits something that makes more electrons, which makes a continuing cascade until you have enough electrons that you can actually see a signal. Now, this device clearly deserved a Nobel Prize, in my view. It's been an extremely important element, not just for particle physics and nuclear physics, but elsewhere in society. Well, they didn't get one. Maybe it's because they were engineers, I don't know. But, I think it's quite curious they didn't. I might point out that recently, even phototubes have been replaced in some respects by the so-called silicon photomultiplier, which is an array of small avalanche photodiodes embedded in silicon. And these have been remarkably successful in converting photons to useful signals in the physics of this current era. Okay. Now in the 30s and into the 40s, one also would find these kind of drawings or images, whether it be proportional counters in various geometries. Here's one with 3 wires, a window here, or 2 wires, or other geometries, even multi-layer things where all the wires were embedded within plates. Now, the common feature of these is that all of those wires were ganged together to produce one signal. But what was understood, though, at the time is that even though the electric field would start out as parallel from the surface of this cathode, it would become circular around the wires. Anyone who's solved those conformal image problems in E&M would understand how that looks. And I'm going to get to that further in a minute, but I wanted to mention something else that occurred in the early 60s. This was first proposed by a Japanese physicist, and it was very popular for about 10 years or so. The idea is that if you can detect when a particle has passed through your apparatus, there's 2 plastic scintillators, not shown are phototubes. There's a coincidence circuit, and then there's a pulsar that produces a big sudden voltage across these plates, alternately producing avalanches and finally a spark. And these were wonderful devices. They made lots of noise. They were fun to work with, and you could make them rather large. I built one for the Seattle World's Fair. It was quite popular. This is a picture of, it's really hard to see here, Mel Schwartz, Letterman, Schwartz, and Steinberger at Brookhaven when they discovered that muons, the neutrinos produced at the target, remembered that they were basically muon neutrinos, and this was recognized in the 1988 Nobel Prize. And so one can see, not so well here, but there's lots of tracks. And they were wonderful devices. But they were quickly superseded because they also had limitations in rate, because you had to clear the ions out from the last spark. That took a while. The pulsar had to recover, and so on. And so what happened was that in 1968, George Sharpak, one of my heroes, realized that one could put all these wires just as before between 2 cathode plates, but now the electronics had evolved to the point where one could hook a circuit to each of those wires and even reduce the distance between them to something like 2 millimeters apart, even less sometimes. So when a particle goes through, those electrons that are closest to the wire would go to that wire, produce an avalanche, and then one could see a signal on that wire and not the others. This is a picture of Charpak, Fabio Sale, and the super technician Jean-Claude Saint-Hilaire, and this revolutionized the field. Suddenly, instead of talking about tens of hertz or hundreds of hertz, we now have megahertz capabilities per wire. It was a true revolution. I've talked about some of this already, but let me just point out that if you have a spacing, say, of 1 millimeter, the RMS accuracy one gets is 300 microns for a single measurement, since it's random population across that. But one can put several of these devices together to get a better measurement of the trajectory by fitting. However, this only gives you one of the coordinates. If you want to get the other coordinate, you can have more of these chambers rotated by something like 90 degrees. It doesn't have to be 90 degrees, but it was typically, you can get the other coordinate. And so this was extremely popular, and I worked with Jack Steinberger to build some of the very first large ones, table-sized proportional counters that were used to study semi-electronic charge asymmetry, which was a wonderful experiment that one could do with half a dozen people. But about that same time, it was recognized that the multi-wire proportional chamber didn't really solve all of the problems, because if you had more than one track, then you would have ambiguous results in a number of combinations. So here I've drawn 6 measurements of track coordinates, 6 horizontal ones and 6 vertical ones. And so you have 36 possible combinations here, and you need to figure out which of those 36 are the 6 right ones. This is known as the n-squared ambiguity problem. Now, it sort of works up to half a dozen or 10 tracks, but the anguish for reconstruction rises even more rapidly, because even if you have other chambers at an angle, often isn't quite clear which is the correct combination. So this was a limitation. Another device that was derivative of the multi-wire proportional chamber in a way was the invention of the drift chamber by Valenta, Einstein, and Schurlein in 1971, and it's illustrated here. Here's our track going again through a device where we know when the track went through with this scintillator or whatever it is here, producing ionization in some volume, which is then drifted over to a wire, and if one measures the drift time of the electrons to the wire, one gets a measurement of that coordinate. However, typically, these drift chambers would be embedded in a magnetic field to induce curvature in the track so that the momentum could be measured through coordination measurements of the coordinates. Inevitably, this introduced an E cross B effect so that the electrons wouldn't go straight to the wire, but they would often, depending on the gas mixture, even curve around and finally land, producing rather complicated waveforms. So the drift chamber was a marvelous advance that led to several discoveries in colliders and elsewhere around the world, but it also had rate and distortion problems, as indicated by the E cross B effect. At about the same time, Wade Allison at Oxford invented something called the ISIS chamber, identification of secondaries by ionization sampling. This device was behind the big European bubble chamber, and tracks that emerged could then be identified by their ionization density, which is strictly a function of the velocity of the particle, whereas the momentum measured in the bubble chamber would be involved the mass of the particle. So they had invented this thing, which is a big bag of argon, CO2 at atmospheric pressure, and they had developed electronics that would take 320 samples of ionization, and in this direction you can see that you're getting many samples of ionization. That could lead to a resolution of ionization density of something like 7%, which wasn't great, but it was good enough to produce some measure of particle identification. What we see in this device, and I've never found a better image of the ISIS chamber that Wade produced and his collaborators, and one now sees that the electronic devices are starting to produce images that look a little bit like bubble chamber quality. So I have to point out that this ISIS device was an important step in the right direction. I didn't know about it, but in 1974, I was trying to figure out how to build some kind of new detector for the Stanford positron-electron accelerator ring, and I was absolutely, completely frustrated. I've been sitting at a drafting table. Most of you have never seen one because now we do it all on the computer. But I couldn't really come up with anything, so the pile of paper was building up on the floor. But finally I remembered that when I was a graduate student, we had another project which had a spark chamber inside a very strong magnet. And when the magnet field was on, the sparks inside the chamber got much brighter and narrower when that was turned on. And this was regarded as a beneficial effect by the group, but not really explored very much because it made the measurement of the tracks easier, but okay, we didn't need to know more than that, but I remembered this. So I thought that maybe diffusion transverse to the fields can be suppressed by what was going on in that spark chamber image. So I thought this might be useful. So I went down to the LBL library and I found Townsend's book. This is the same Townsend who worked out the physics that Rutherford and Geiger used. And the book had the right title, Electrons and Gases. So I took it, and someday I should return it to the library. I have to admit I still have it. And on page 20, you can find this image here. This is the diffusion, and it has this factor, which is the mean collision distance and the speed of the electrons divided by 3 for one of the 3 spatial coordinates. Then there's this factor in the denominator, 1 plus omega squared t squared. And this is what I was looking for. Omega is the cyclotron recession frequency of electrons at something like 10 to the 12th radians per second strong magnetic field. And T is whatever it takes for an electron to run into another atom or molecule. So that's the mean collision time. That's a pure number. So if T is long enough and omega is large enough, then you can get a number that's bigger than 1, and voila, the diffusion might be suppressed. So that was interesting. But the other thing that was amazing is that this book was published in 1948. Apparently I was the first person who read this book. But I was the first person who noticed it. However, the situation is actually much worse than that. He published this same thing in 1912 in the Proceedings of the Royal Society. And I found that paper too. And here it is again. So apparently I was the first one to notice that this might be a useful thing. It's incredibly simple. Conceptually, we just imagine that the electron is rotating around the magnetic field before it hits something. That suppresses the diffusion transverse to the direction of drift. So that could be useful. So I think this is remarkable because it was really quite at the time, something that was completely unknown. So I understood what I needed to do. I needed to get something, some experimental situation with omega tau was greater than 1. So how do I do that? I discovered that in argon and methane, there's a sharp minimum in the electron atom cross-section around a quarter of an electron volt. That's shown here in this old plot here. So one sees the cross-section goes down and then it goes up again for both of these molecules around 2/10 or 3/10 of an electron volt. That's a bit above room temperature energy, but it's still something that you can control because this is the cross-section of electrons in methane for inelastic cross-section, so you can keep the electrons right in this energy range because if they gain too much energy, they're going to be losing it in collisions. So one has to just find the right combination of gas density, gas mixture, and electric field, and you can park your moving electrons right in this minimum. So this is providential. I mean, here nature has given us something that one didn't expect. Here's quantum mechanics in action. This is really just the potential well where the forward scattering is where you get the positive reinforcement. So the argon and methane kind of disappear at this electron energy. And it turns out that even at 8.5 bars of pressure, because we wanted to do the same thing that Wade Ellison did to measure the EDX and do particle identification, we would still get omega tau greater than 10. And what this means, since it enters in the denominator as the square, I could now drift a meter and have the same quality of information as if I just drifted a centimeter. So the effect of diffusion was really highly suppressed. And now we have the possibility of a detector with nothing in it except gas and magnetic field and electric field. This is very different from other detectors which had lots of wires going this way and that. So this was new. And again, this is a providential bit of quantum mechanics in action working in our favor. So then the next problem to solve was if I'm able to transport these track images, how do I read them out and preserve all this information? I could have a readout plane that had good XY information, and then if I measured the time, then I would get the third dimension, and the raw data would be intrinsically 3D. And so I thought that maybe I should call this the time projection chamber. And so this was in 1975. I think we were a group of 4 trying to figure out how to make use of these ideas. I got a phone call. I think it was a vice president at General Electric, the vice president in charge of reading everything. And he said in hushed tones, "I hear that you have invented a time projection chamber. Please tell me in which direction you have gone and how far." And I didn't have the wit to ask him, how much is it worth to you? But instead, I just told him what it was, and he was very disappointed that he couldn't do it. Anyway, those were exciting times. This story got around, and I gave a colloquium at Harvard, and Steve Weinberg introduced me, and he remembered this story perfectly, so I didn't have to use it myself. So we were fooling around with gases and magnets, and we built this little thing that could fit inside one of those standard bending magnets. An alpha particle starts up here with emit many electrons, and we arrange it so that only one electron would fall through a tiny hole and then get drifted down. And then we map out its position of arrival down here with this micrometer. And we verified that, in fact, Townsend was right. He understood everything, and it was something that we could use just as he described. This is a beautiful device, and it still exists. And I wanted to mention that if you have good engineers and good technicians, they're just tremendously important for success because this stuff worked for the first time. So anyway, in 1974, we proposed to build something that's 2 meters in length and about 2 meters in diameter, with readout planes at the end, schematically indicated here with wires and symmetric one with a cathode plane in the middle. This device was actually built, and after a lot of struggles that worked just as one planned, we could actually measure the drift time to a precision of 1 nanosecond RMS, even though we wouldn't have expected such good performance, and the DDX was the best I think anybody has ever done. So it was a success story, but it was a struggle to get everything to work, and I don't have time to go there. But again, this is one of the TPC sectors. There are 6 of them at each end. You can see the reflection of the light on the wires, and then behind the wires you see the 12 pad rows, which gave us the coordinates of the avalanche along the wires here. Again, these were beautiful instruments, and I managed to preserve one, and it's really wonderful. So, then we had another problem, which is how do we read this thing out? This was 1970s, and things were really quite different then. We had transistors, these little black things with 3 legs. Integrated circuits were just coming into existence, and we had too many channels to use the same kind of electronics that Wade Allison had used, the sample and hold circuits. So how would we do this? So we had an idea. Let's use something called continuous waveform sampling. Remember that Wade Allison would wait for something to happen, and then he'd store that time and store that pulsar, and then digitize it later, but in no sense was it a continuous capture of information. And about this time, a newfangled device, electronic device called the charge-coupled device. This later was recognized for the Nobel Prize, but the devices at that time were simple, linear electronic things, not imaging devices. They were used as variable delay lines because you can vary the propagation time through it by the clock speed. So we thought, okay, let's capture the information coming off our readout lens at this incredibly high speed of 10 megahertz. And then when our trigger occurs, we could digitize it much more slowly because we didn't really have fast ADCs at that time. So this sounds quaint now to talk about 10 megahertz as a high speed and 1 megahertz as a digitization rate that was difficult. But that's the story it was. However, when we actually used these devices, they didn't work because they didn't like to have the clock frequency switch from the 10 megahertz to less than 1. Now, as an indication of the time, we simply drove down to Fairchild down in San Jose and said, how about this? And they said, okay, we'll redesign it for you. So they did. They had to redesign the internals of it so there wouldn't be any sharp corners which would cause a problem. So we got these new devices from Fairchild, and they were an essential technology for the success of PEP4. And I do think that PEP4, the TPC, was the first to use this continuous waveform sampling. And now we see these iconic pictures of the heavy ion collisions everywhere, coffee table book covers, and also covers of DOE agency reports. And they're certainly beautiful things to look at. I find this one from at least rather scary, but possibly they can figure it out. But my favorite event in the TPC era is this one from STAR. This is the production of an anti-hypertriton followed by a decay to anti-helium-3. So despite this maelstrom of tracks, here we see it in 2D, but of course the TPC gives it to you in 3D. You can figure out what's actually going on. So many applications of the TPC were then developed by others far beyond what I had ever imagined. And I went on to work in other fields for a while. I'm going to talk a little bit about DUNE, the deep underground neutrino experiment, and then also a little bit about NEXT, which is something that's being led here by the IFIC group here. Not enough time to talk about all these other possible applications. Let's move on just for completeness, though, to talk about the so-called micro-pattern gas detectors. One of them, the GEM, shown here, was invented by Fabio Sale, a piece of double-sided copper-coated Kapton film with holes etched in it, and with a sufficient potential across these two foils is applied. Then one can get avalanche gain and actually see in great detail tracks as indicated in this sketch here. You can see the depiction of the avalanche going on in the gap. Another related similar device was the Micromegas, which had a screen or a foil supported by posts, also a gap of just a fraction of a millimeter. And these devices have also been quite productive. The problem is that if one gets a spark, copper can melt if you have a large enough device because of the stored energy. And there are other configurations that one can imagine which all have the primary goal of increasing the electric field so that one can drift information down and get an avalanche gain and hence a visible signal. Now the smallest of these is the so-called GridPix micro TPC proposed by Harry van der Graaf in Amsterdam. And here you see this colorful image of the track going through, and then avalanches occur as the electrons are drawn through this grid, all made by lithography. That has an active mass of 10 milligrams. At the other end of the scale is the deep underground neutrino experiment, which has 5,000 tons of liquid argon. 2 of these make 10,000 tons, and 4 of these modules give you 40,000 tons of liquid argon, which is the goal of the deep underground neutrino experiment. So I think no other detector can claim a working mass ratio of 10 to the 12th. So for what it's worth, I thought that was amusing. Now moving on to a scale which is more familiar on the order of kilograms. This is from the NEXT collaboration, real data from a cesium gamma ray, which has 662 keV, entering a TPC, and what one can reconstruct in 3D, shown here in various plots, is the actual track, even though it scatters quite a bit in the xenon. And one sees that as the track runs out of energy, as the electron runs out of energy, there's more ionization density near the end. So we would call this spaghetti with one meatball. Since we are looking for double beta decay, hopefully zero neutrino double beta decay, and the transition of xenon-136 to barium-136, we would then have spaghetti with 2 meatballs, and the TPC can give us extremely valuable topological information to discriminate against gamma ray events such as this. Now, I'm not talking very much about NEXT in this talk because it's so familiar to people here in Valencia, but this shows another, I think, way that the TPC has evolved and is producing perhaps the most powerful technique in the search. Related to this is another new idea, and this is something that I want to illustrate as an example of knowing something other than what you're used to can be very helpful. In 2014, the Nobel Prize in Chemistry was given to 3 physicists who worked out this super-resolution microscopy and single-molecule fluorescent imaging. So this was a foray of physicists into biology, and what they were able to do, along with the work of many others, is to see what's happening inside living cells by tracking individual calcium ions, which are everywhere. But if they're connected to one of these fluorescent molecules, you can watch them move inside the cell, far exceeding the diffraction limit by repeated sampling. And the way to know that you are dealing with a single barium or calcium ion is to look for a transition in which the molecule bleaches. This is sometimes temporary but often permanent, where there's a single step function to the background level. So we were able to reproduce this, and this is a plot of a single barium ion seen with about 13 sigma, with about 2 nanometer localization. And this is possibly something that will be essential for a robust discovery of this decay, because the gamma ray cannot produce barium from xenon. The probability of that kind of transition is negligible. So this allows you to claim that the event you would see, if it really is a barium body, is a true double beta decay and not something induced by that. Okay, so we're getting to this slide which illustrates the 4 epochs that one could imagine. Talked about the early discoveries stimulated by meteorology, the era of single particle detection in various ways, from the spinthariscope to the Geiger counting, typically done by amplification through avalanches. Finally, to the golden age, realized by the multi-wire proportional chamber, the micro-pattern gas detectors, TPC, drift tubers, etc. So now we're in the megalithic age, and what does this have that serves the purpose of a talk like this? Because things have really changed. So the first megalith of this era is that comes to my mind, is the Auger Observatory in Argentina. This is a 1,600 water tanks looking at the debris of the shower, looking for the highest energy cosmic rays. Also seeing the fluorescence imaging in a way to see the track itself. And the energy would be measured down the surface by these water tanks. So the combined measurement of the fluorescence and the water tank gives them a way to calibrate, looking for events on the order of 10 to the 20th electron volts. Of interest here, though, is what are these tanks? The water tanks are permanently installed with 12 tons of pure water. There's electronics, GPS antenna, and then communications, and so on. So this is a completely autonomous unit. It keeps its own time, stores its own data, and transmits it to the central data acquisition system. This is what's happening more and more, is that we can devolve the function to the periphery. That brings me to the second megalith, the ice cube observatory at the South Pole. And there's another lesson here, which is how one thing might lead to another, and I'll get to that in a moment. So the ice cube observatory is a second generation follow-on after the first one, Amanda, which is this little part of the present ice cube right here. That's the Eiffel Tower for comparison. A cubic kilometer of ice has been instrumented by strings that include about 60 optical detectors per string. There's a surface array as well. But in Amanda, the signals were sent over coaxial cables or a twisted pair to the top. And the signals were vastly degraded. They were stretched out in time and diminished by resistance of the cables, and all of the complexity of the signal was lost. And in going now to $200 million project, we wondered whether it's possible to go to a low-power, decentralized digital network in which most of the functions would be done in the ice forever permanently. This was kind of a radical notion at the time. It wasn't sure that one should do this. You're making a $100 million bet that you can make all this work, because you can't undo it. But one thing we didn't have at the moment we were thinking about this is, how can we actually acquire this data? We wanted, because of the tremendous dynamic range requirements, we needed something like a 14-bit, 400 megahertz ADC, and this was simply not available where it would have been very powerful as well. Here again, we were aided by a single device called the Analog Transit Waveform Digitizer. Before I get to that, let me say that actually IceCube was successfully implemented with 86 strings, and all of these digital optical modules have complicated electronics I'll allude to in a minute. And they have been extremely reliable. Only 1% of them have actually died, and about 1% was also lost just by bad connectors. So let's see what's going on inside. A single electronic chip made IceCube possible as we know it today. So the $200 million bet was won because of this particular integrated circuit, which was the analog transit wave recorder, not digitizer. This was a master's thesis project that Stuart Kleinfelder did for engineering at Berkeley. And it basically just captured waveforms and stored them on an array of switch capacitors. You can even see the structure. There's two identical sections here. And they were capable of sampling at something like 200,000 megahertz. Each one of these three channels could have about 10 bits. So by stacking the gain of the digital channels, we could get to 14 bits. I actually had to track down Stuart at the grocery store and say, Stuart, you have to add the ADC, and he did. And so finally we were ready. And it was really one of those kind of comic stories in which you're trying to do something and you have to depend on somebody to do something who really doesn't have to do it, but he did. So we got this chip that was not just the analog transit wave recorder, which would have required an external ADC, but actual digitizer as well. So what's in those optical modules is this. I'm not going to spend much time. Here's a phototube, a 10-inch phototube that captures complex optical signals. And then these are converted to analog electrical signals that are stored. We actually put two of these chips in because we were worried that one of them may die. So we put in two just in case, but they don't die, so we're in good shape. But there they are. And then lots of complicated stuff happens inside the field programmable data array. Finally, packets of timestamped waveforms go out here on this to the surface. So this was a lossless information capture. We actually were able to get all the information that the phototube could produce, and lots of stuff what's going on that we don't need to talk about here. But one of the interesting things was this oscillator here. This ran at about 10 megahertz, and it was a commercial device built by Corning. We paid about $60 for each of these things. The original device was a $5 part from Toyocom that had incredible performance. It almost behaved as if it was one of the rubidium stabilized clocks, but it was built according to Radio Shack standards, so we couldn't use it. Anyway, so that's an aside, but the point is that the digital optical modules were, again, completely autonomous. They kept their own time base, and we would just periodically ask them, well, what time do you think it is, and please send up your data. And now, everybody thinks that's obvious. Works perfectly, nobody thinks about it, but it wasn't obvious at the time. So I'm going to probably skip this, the details of this slide that tells how we actually measured the time and measured the timing of the time it took for pulses to go up the cable and back. In any case, we were able to time up this cubic kilometer of ice to about 2 nanoseconds. The critical part of that was that the oscillator had to be stable to about 1 nanosecond per second, so that we wouldn't have to interrogate it too often to find out what was going on. All that worked. So, in retrospect, it was a single device that really made it possible for us to promote the idea and develop it. Now, just to close that story, IceCube is capable of detecting these huge events. Shown here, there's several of these which are PeV energies deposited in the ice. The red color means early and the blue color means late. The size of the blob is the energy deposition. So these make beautiful images. If you superimpose them on the city of Madison, you can get an idea of how much light is being produced in the ice. Down deep, the ice is extremely clear. It scatters, but it doesn't absorb, so you get these rather complicated events. So I should mention that IceCube has also been able to detect the direction of neutrinos that turn into muons, and hence point back to blazars that are possibly the source of these high energy neutrinos. So now I want to take the last few minutes to talk about how this idea of functional devolution might be used elsewhere in another different kind of application. Going back to the deep underground neutrino experiment, doing this the third megalith. These are huge. Don't think there's any humans indicated on this scale, but these are many meters high and many meters wide, hold 40 kilotons of liquid argon. So the challenge here is how to get this information without degrading it. The current plan is to drift the electrons to planes of wrapped wires. These are similar to the, in concept in a way, to the multi-wire proportional chamber, in that you get one dimension because the wire is extending so far. You have to have several planes in order to reconstruct what's really going on. It doesn't work perfectly. And spatial projections can lead to those same kind of ambiguities that I mentioned earlier, that the TPC was intended to resolve. So some of us are now attempting to pixelate Dune. This would again give you intrinsically 3D raw data. Wouldn't have to worry about interpretation. This may make this attractive. I'll show it a little bit why I'm thinking how this may happen. For such a large detector, most of the time nothing happens, but then when something does, you have to recognize it. And can you make it so robust that you can never have to worry about tending to the electronics because it's buried forever in liquid argon? So we're developing something called QPix, which is a novel and apparently new way to capture waveforms. And again, we are pushing all of the functionality down to the sensor itself, just like IceCube. Now, I don't know whether we're going to be successful because we're intending to disrupt the current paradigm of Dune. We're not part of Dune. But I do think it's worthwhile to take a look at how one might think about the problem of a huge detector. Most of the time, nothing has happened. But how do you deal with that? And this is probably the most elementary kind of electronic circuit that you can run into these days. This is a charge-sensitive amplifier. A signal will arrive here, and the signal will be integrated onto this feedback capacitor here. And then, if the signal is large enough, it will trigger a response in this thing called a Schmidt trigger, or a comparator, which will make a complete transition and reset that charge on that capacitor. So the only thing that's going on here is continuous integration here, and the occasional transition here, which resets it. That's about as simple a circuit as you can imagine. So how do we use this? If we also couple this to an internal clock that keeps time in whatever time units it has, and whenever something happens, you just store that time, and that's it. That's your basic data. So what's happening here now is that you are measuring the time between a certain charge, so that we're measuring time to charge, whereas typical digitization measured charge per fixed unit of time. This is just the opposite. And this seems to be novel. We claim that waveforms of any complexity and length can be captured this way. So we've done some simulations. This is a waveform in which the current arriving at the input is shown in this purple line here. Here is showing the transitions of this simulated circuit. This is probably an artificially low threshold. Anyway, you see also the Schmidt trigger output. And you can reconstruct in the green, barely visible here, what the waveform was. So we claim that we can capture all of the information even with this entirely simple circuit. You would imagine then that the dune would be papered with these tiles about 1/4 of a meter by 1/4 of a meter with all of its integrated circuits. Each of these yellow ASICs, application-specific integrated circuits, has its own clock, maybe running at about 50 megahertz. We don't care what that frequency is, as long as it's stable, 1 part per million over a second. Everything that's novel about this is that each of these integrated circuits is connected only to its nearest neighbors, and they talk to it and they work out their own network once you ask it to assemble itself. So this is new too. It's not really new in the sense of the network theory, but it's new in high energy physics. The point here is that if any of these chips fails, it will find a way around it. In fact, it plays its own game of Go in order to establish the network for data acquisition. So this is going to turn out to be an interesting project. The DOE will probably support us, and we'll see what we can make of it. I mentioned that here we only need a part per million since we're given 1 microsecond rather than 1 nanosecond. So we think that the clock inside each of those ASICs will be stable enough. Now, is it possible that this way to capture waveforms is new? I don't know the answer to that. I've never seen it, but I think it's new. And maybe it will turn out to be a kind of enabling technology for Dune to really become a discovery machine, because we will extract all the information without any ambiguity if we can make this work. So it's going to be exciting times for us ahead. So getting to the end here, we saw that one of the epochs was where we were finally able to see the impact of individual particles in the cloud chamber. There were spark chambers, there was nuclear emulsions, and finally the revolution of the marriage of electronics to gas detectors, and other aspects too that I didn't talk about, the silicon strip detectors and so on. So we don't know, I certainly don't know how the future will evolve. The LHC high luminosity era needs extremely high resolution and an extremely good time resolution in order to separate the multiple interactions per beam crossing. I don't know how that's going to happen, but it's not going to happen with conventional electronics. Something new like optoelectronics or spintronics will be necessary. So there are still opportunities. I think that that's the message here, is that if you know something beyond your computer screen, you might find a new way that you hadn't any idea existed. It's also clear that some good ideas are missed, or that's by the lake. And I think that the future will show us that there really are new opportunities. Mueller paid attention, that was great. And the engineer that has some ideas can also be the thing that makes your career, and so on. So I think that the history shows that really new ideas were possible and probably still will be. Thank you.
We have a few minutes for questions.
I know you were all awake because I was watching it.
As usual, let me warm up the atmosphere. You just made this last comment that discovery, in particular in our field, may be fully connected to having around the exceptional engineer.
Yeah.
Actually, it could not agree more. And in Next, we have seen that one day after the other.
Yeah.
Perhaps in the US system, there is a way to integrate engineers into science. In Spain, or in Europe in general, it's not very trivial. What would be how do you actually incorporate the smart engineer into the scientific system? In a system that tends to separate things, right?
A very good point, and I don't have the really good answer for you. I think that what happens is that people who appreciate good engineers will attract them and keep them. Even in the US, in the old days at Berkeley, engineers were valued but still treated as second-class citizens because of all the heroes that were running around Berkeley at that time. But I think since then that has changed, and right now the utility of engineers is appreciated, but I think there's no magic formula that I have for that. I think it's critical. I wanted to emphasize that, and I'm glad you did too.
My personal impression is unless we radically change ways here, we may get stuck, because it extends not only to engineers, but to the kind of thing you also said. I don't like the word instrumentalist.
Yeah.
I don't like it either, but it's often used.
Yeah.
And basically progress in particle physics depends on having engineers, on having people understand detectors. Both of them are treated as second-class citizens, and that is a danger, actually.
Yes, I think that's true, and I think we should now keep in mind that we live in a highly technological age. All of us use gadgets, we have no understanding what's going on inside. Very different than the early era where you could and did.
Thank you. More questions?
There's one.
I'm sorry. So regarding the QPX, that novel waveform sampler, what will be the expected bandwidth, I mean the frequency bandwidth?
Well, it's hard to answer that, but I think that we think that if you have a 100 megahertz clock shared among 32 pixels, say, the power dissipation is adequate. But your question is the analog bandwidth. I think that again, you pay power for more bandwidth. I would guess that the bandwidth is still around 10 megahertz, which analog capture, 10 to 20 megahertz. Otherwise, you're going to pay more power in the front end.
One more question before we start.
A troublemaker in the third class.
So you mentioned the return of the bubble chamber in liquid xenon. So I know which bubble chamber you are not speaking about, but what's the idea? The idea is that a nuclear recoil would create a bubble where an electron recoil will not.
That's correct.
And then you need to expand somehow, make the pressure drop so there will be a S1 trigger that will expand the...
These bubble chambers are continuously sensitive and just have to be the right temperature and pressure so that a certain energy loss in a small enough volume will trigger a bubble formation.
So if you just take liquid xenon and a nuclear recoil in it with no external interference, will it give you a bubble?
That's right. That the nuclear recoils do give bubbles and the electron recoils do not. It's true.
So I'll take for coffee.
Yeah. This has been pursued at Northwestern University by Dahl and collaborators.
Okay, unless there is an urgent question, I think we should thank the speaker again for an excellent trip through the art of the experiment. Thank you very much.